cardiac.
Different names um, here. And so this is what, this classroom will also have issues with Wi-Fi on my computer as well. All right. So So that's who we are. And the second question I asked is about what's your favorite topic in computer science? And apparently, there is a long list, but as a computer science, as a data scientist, you should definitely know how to visualize your data. So this is what we learned. So from this figure, you can see that 42% of you are interested about AI and machine learning, and 10% of you are interested about security. 13% of you claim that you are interested about embedded systems. Well, then operating system, high performance computing, distributed system, each has 3%. Computer architecture, well, not too bad, about 10%. But there is no doubt that computer, in terms of artificial intelligence and machine learning, they are the most favorable topic from you. Now, the third question, which is the real question that I want to test your academic integrity. So turns out that a lot of you think that you are interested about computer architecture, which I think I will give you a cheat on that. But for some of you, I do see some keywords from the word cloud that I generated. You take computer architecture because it's a core course, because it's a required. I hear you, right? So today, my duty here is to give you some incentives about learning computer architecture. So so we have learned a lot about you. So now how about me? So your instructor, I'm Hong Wei, and I'm an associate professor at UC Riverside. Here's my website. And previously I was working at Google in the past 3 months, and it was a very good experience. I gained a lot of weight there because of the free food. I work for TensorFlow Lite team, which is one of the organization under Google Core. And so you know that I have a lot of experience in developing this AI machine learning infrastructure. So I'm qualified to tell you a lot of things about what industry people really care about and how things work out in the company. And before that, I was a PhD student at UC San Diego, and I'm interested about general purpose computing using AI ML or accelerators, and I also build intelligent storage device or anything else that is fun. For example, in my lab, we used to build a framework with untethered VR system as well. So that's who I am. So one thing that significantly changed my life in the past 3 months. So sometimes I feel it's kind of a blast that I was at Google at the time, that it was a really interesting period of time. So for example, I was experiencing the first ever large-scale layoff at Google. So one thing that I can tell you, the most significant change that I can feel is that before the layoff, every evening when I go to the cafeteria, when I want to pick up a food, I don't have to be in a line. But the next Monday, because typically people would lay off on Fridays. So the next Monday, when I try to put myself in the line for the dinner, it takes me about 30 minutes. I always go at the same time. And so we have a team lunch. Before the layoff, there are only 6 people showing up. Right now, and the team lunch after the first layoff, I figure out that we have 30 people at least. So everyone is kind of back to office. And then almost about the same time, like Microsoft, they have a pretty good presentation on ChatGPT. And then everybody is thinking about, well, what's Google's response on that? And apparently a lot of the story you guys know, right? We bomb it. And so then the whole company is shifting direction in a way that we call it refocus. We are refocusing back on AI ML stuff, and everyone is kind of like tied up. And it used to be like people feel that Google is one of the most laid back company in the Bay Area, but turns out that now every of my colleague, they have to work very late. So that's why we have a line in the dinner. So ChatGPT changed our life, but I have an introduction that I wrote for myself. I'm a PhD at UC San Diego, and let's see what ChatGPT know about me. Okay, so the first question I asked ChatGPT is, who is teaching CS203 at UCR? So see, I'm giving ChatGPT some hint. So the ChatGPT is saying that as an AI language model, he has no access to real-time information. Who is teaching CS203? Is that true? That's not true, right? Like you can see it online and it's open to public. And now the second thing, okay, let me give ChatGPT some more hint. Who is Hongwei Zhen? And apparently he has no comment on me. He doesn't know me. Fine. Then who is Hongwei Zhen at UCR? Okay, some more information. Associate professor at UCR. Research interested in the area of computer networks, distributed system with a focus of improving network performance and security. Is that what you heard from my introduction just now? Okay, and then some of his recent research work has focused on topics such as network measurement and monitoring, network optimization, and network security. I promise I have never done work like this in the past few years. And has been a faculty member at UCR since 2013, which is the time that I haven't got my PhD yet, and I don't know how can I be employed by UCR at that time. And he received several awards and recognition for his research contributions. That part is correct. But you know that a lot of stuff that ChatGPT is trying to tell us is not true. And in fact, a lot of information you can just copy and paste from the website. So if you try to use ChatGPT to do your homework assignment, that's what we end up with. You are not getting right answer most of the time. And as a Googler, you definitely want to try out our product. So the second thing that I try is Bard. So I asked the same question, exactly the same question to Bard. Who's teaching CS203 at UCR? Okay, it thinks a while, about 3 seconds, and then it gives you an information. And he say that Hongwei Chen is teaching CS203 at UCR. That's correct. And assistant professor at CSE, yes or no? Because I guess it got the older information, but mostly is correct. Then I asked like, I think I should stop here. Then I asked another question. Let me see. What's the? Sorry about that. It's not. Let's stop here. Okay, and well, give it a second. So yeah, I asked the same question to Bart, who is teaching CS203 at UCR. And apparently, it's getting me some of the wrong information. For example, it tells you guys that I'm a PhD from UC Berkeley, which is definitely not true. And I am proud to be a Trident rather than a California Bear. And okay, so for who is Hongwei Zhen, I think Bart did a good job in a way that it tells everything here is correct. At least it knows how to Google, right? So that's the thing about this AI models, right? And the generative AI models. Okay, so that's something that I learned from ChatGPT and Bard these days. So now another question that I ask you guys about is what? Okay, so regarding your favorite topic, right? We already know that 42% of you are interested about artificial intelligence, this kind of stuff, and many other stuff. So in general, here's the conclusion that I have for you, right? So regarding what you care about as a computer science and engineer, you care about artificial intelligence, you care about machine learning. A lot of you saying that you are interested about stuff like software engineering or programming language or even UI design, right? But this is your attitude. Because I don't care as long as you just hold me. Today I want to change your idea about computer architecture. So first of all, why should you care about computer architecture? Okay, so that's the first question that I want to ask about. So a lot of you saying that you are interested about AI and machine learning. So what's the fundamental of modern AI machine learning? What's the fundamental stuff that power the recent AI and machine learning? Can some of you tell us? Linear algebra, okay. A little bit above that label. Regression models, okay. Linear regressions, what's your name? Xiao, what's your name? Jingong, okay. What else? It's not that difficult. We mentioned it before. What was that? Like, okay, most of the modern AI ML models are based on autocomplete. What are the words that the term that you are going to put here? Neural networks. What's your name? Selenia. Serenia. Okay, I hope I got it right. Okay, neural networks, right? So who won a Turing Award on neural networks? Who got Turing Awards because of the advancement of neural networks? Do you guys know? Like, okay, so if we want to say who is the father of neural networks these days, who are you going to think about? Ask ChatGPT now, or? There was a competition for it. No, I'm saying about like, okay, if I want to say who are the most iconic persons in neural networks, then what are the names that would pop up in your mind? What? It will be on the slides. No, that's not. No, Turing is the very ancient one in computer science in general, right? Like if I want to say who contributed to the recent advancement in neural networks the most, who are the persons that you have in mind? Geoffrey Hinton, okay, right. So Geoffrey Hinton, he actually
credit for deep learning really goes to the people
actually
who
got a
collected the big
Turing Award in
databases like Fei-Fei Li, and the people who made the computers go fast, like David.
One
I
more
think
time.
a lot of the credit for deep learning really goes to the people who collected the big databases like Fei-Fei Li, and the people who made the computers go fast, like David Patterson and others.
Okay, so this is part of his Turing Award speech in 2017. And one of the slides, he mentioned that, well, you know, people like to be humble, and Geoffrey Hinton is definitely one of the person like that. And he said that a lot of the credits of deep learning, or say neural networks in general, is because we have large database like people like Fei-Fei Li, and the other is David Patterson and others who make the computers go fast. So who is David Patterson? What? The author of your textbook. Okay, guys, have you purchased the textbook yet? So David Patterson is the guy in the middle, and together with John Hennessy, they wrote the computer architecture textbook that you are going to use for this quarter. And there is some familiar face that you will see on the right-hand side of David Patterson, left-hand side of David Patterson. That's actually me, right? That was in 2018 Turing Award ceremony. And So if you want to figure out, if you want to know more about what David Patterson or John Hennessy do, you will find out their name is actually on your textbook, the computer architecture textbook. So let me quote. So combining with everything that Jeffrey Hinton said, and you know about David Patterson, here's the conclusion. Computer architecture actually enables deep learning. So without the contribution in the area of computer architectures, there is no way that modern deep learning or deep neural networks in general would work. All right, so then I keep asking ChatGPT about another question, right? Let's see what ChatGPT said as an AI model. So I asked, how important is computer architecture in computer science? Okay, so this is what ChatGPT throw me an answer. Well, you know, one thing I don't like about ChatGPT is that it tries to tell you a lot of things. But one thing that you could notice is that, okay, computer architecture is a fundamental area. Anyway, computer architecture is an essential area of study in computer science. That's the conclusion, right? It's very important. All right, a lot of you are interested about AI ML. So let's ask ChatGPT again. How computer architecture is important to AI ML? And yes, computer architecture is important, right? So this time it just directly throw you an answer, yes or no. It's yes. Okay, so like GPUs, CPUs, they are important to the computation that you need in in AI ML. All right. The answer is too long. All right. So, but great answer. Okay, again, SBOT. How important computer architecture in computer science? All right, take a while, but it gives you an answer, right? So in conclusion, computer architecture is a fundamental field of computer science that is essential for understanding how computers work. And it's also important for designing new computer systems and improving performance for existing systems. How important is computer architecture to AI ML? Computer architecture is important to AI ML because it's a fundamental on which AI ML systems are built. All right, so we know ChatGPT and Bard, they make a lot of mistakes, especially things about me, but at least both of them agree on one thing, that computer architecture is important. And in fact, without computer architecture, there's no way that Bard or ChatGPT will work out. All right, so some of you might have that fundamental question. I bet a lot of you are master students here, according to the survey, right? So you might be interested about that. Well, I know computer architecture is important, but will that give me a job? Right, that's the most fundamental question. So we are now actually at the new golden age of computer architecture. So like Google is making a big move in silicon that could scare NVIDIA. We built TPU, and that's why they hired me for TensorFlow Lite, because part of my job is trying to make more efficient use of tensor processing units in the TensorFlow infrastructure. And well, you know John Hennessy just now, right? And John Hennessy is an executive chairman at Alphabet company. And if you don't know who is Alphabet, it's actually the parent company of Google now. And it's also the parent company of Waymo and many, many other small Google stuff. And even at Amazon, so by the way, Amazon is now holding 3% of the market share in the global chip market because they are actually producing their own chips for data center servers. And not only Amazon, you know that if you have an Apple device, they are all using their own chip for now, right? So it's definitely another example that are hiring people to produce hardware chips. And everyone are building chips, right? And so you know that there is a big job market there in computer architecture, not only hardware design, but also everything built on top of that. So computer architecture is actually a very important class of, I would say, underrated area of study, and a lot of people are so fascinated about the AI/ML part, but forget about that. Everything about AI/ML need a computer to power it. Now, let's go back to the AI explosion, right? So actually, ChatGPT and Bard, they are leading a new trend of AI/ML evolution, and actually it stimulates the compute demand. So some of the news that I got recently, like for ChatGPT, like training a model, you will need thousands of NVIDIA GPUs, which are very, really expensive. And for Bard, we use tons of TPU to do that. And in fact, because those models are large, so you need memory to store it. So another news you will see is that companies like Micron, people used to think they are dead, but right now they are revived because the huge demand of memory. So, well, some of you might have that in mind. Okay, I just want to have an easy life. I hate those AI stuff. Okay, I want to be a gamer, right? But don't forget, before the AI explosion, right? Gaming is actually one of the fields that stimulates the demand of purchasing GPU. And in fact, GPU were designed to have your game running smoothly, right? So if you are interested about being like designing game or making good graphics, right? No matter it's on very hardcore TV consoles or high performance computer or even a mobile phone, right? Everyone is everyone would like to play a game at some point, right? So but everything that will make your game experience better relies on how we know the computer works. All right. So now, you know, computer architecture is important. So what is computer architecture really about? So that goes to another question that I asked on the questionnaire. What is your impression about computer architecture? So here are some of the keywords that I heard. A lot of you still have the impression about it's about hardware, but regarding hardware, memory, CPU, cache, processors, those are the stuff that you previously pick up in computer architecture. You are not too far away from it. That's really computer architecture about, and in fact, those are the main components we have in computers. But why? But why this component? And what is computer architecture? So those are components, right? So what are the big picture of computer architecture? So computer architecture, if you go to the dictionary, it will tell you it's the manner in which, look at the fifth one, it's the manner in which the components of a computer or computer systems are organized and integrated. So, so you know that there are tons of components that you have in mind. The art of combining them together is actually computer architecture. All right, so now I'm going to give you 3 minutes to talk with your friends to remind you something about how does a computer execute a program. Talk with your friend in 3 minutes. Hello. All right. So what do you guys have in mind? What do you guys have in mind? How does a program being executed on a computer? How can your computer run a program? What's your name? George? Jordan. Okay. What's your idea about that? Assembly code, and then okay. There's some magic that will process your assembly code. Okay. Any add up on that? Anything you like to add up? Okay.
That takes the assembly code, takes the one line of instruction, and then there's a component that interprets it so that the right components are activated.
Okay. What else? So there is a component, interpret your instruction, and then
Activates the right components to execute.
activate the right components to execute. Okay, what is that component? I heard some word. CPU processors, right? Okay, what else? Memory. Okay, how are we going to use memory in your when we run a program? It will be loaded into the RAM, and then fetch the instructions from where to where? To memory, from memory to CPU, right? All right, what else? The program counter keep tracking where you are in the program. What's your name, by the way? Aaron. Okay. All right. So we got a few feedback from you guys, right? So here's the big picture, right? Here's the big picture of computer architecture. So the big picture of computer architecture is actually coming from John von Neumann. So John von Neumann actually defines how modern computers should work. And here is what he said. Well, so a computer should have this three parts of the main components. One is the storage, which give you a persistent storage of your data and code. If you want to execute a program, so in the very beginning, right, your programs will be put into the persistent storage. At the time of John von Neumann, it's probably like those punch cards, right? And then when you want to execute a program, load the program into the memory. And the program, each program actually contains two parts. One, a sequence of instructions, or you can consider them as commands that you want the computers to do. And the second part is the data. When you want to execute a program, you load the stuff to the memory, and then a processor will fetch an instruction pointed by program counter, as some of you mentioned. So we fetch the instruction at a program counter. The program counter is in fact the memory address. We fetch the instruction from that memory address, look over it, and see what the instruction want the processor to do. So that's the big picture of execution. And then if the instruction want the processor to deal with data, that's the time the processor will fetch your data from memory. So this is the von Neumann architecture. So as you can see, in von Neumann architecture, the good thing about that is that by loading different programs into memory, your computer can perform different functions. So that's a good thing about von Neumann computer, right? And before the introduction of von Neumann architecture, most of the computers, they only have fixed functions. it's typically like a slot machine in Las Vegas in a way that, well, if you go to the slot machine, you can only play this game. You cannot have options that I want to do other games, right? But with von Neumann architecture, what would happen is that you can load any program into the memory, and the processor just looking over what the program wants us to do, and you will do whatever you want to, whatever you give the features to the program, right? So that's the von Neumann architecture. And as you can hear, right, those components are pretty common in computers. So, so first of all, if you have a desktop computer, right, if you tear it down, you will see a motherboard like this. I have one here for you, and this is a computer that can still in use, so be careful about it. I was spending trying to figure out how to take this down, but apparently I am not really successful to take this down. So, all right. So, okay. So here's the computer, and under this heatsink, there is a CPU socket where you can find a processor like this under this heatsink. And there is another area that you will see here is actually for memory. So this area is like a few memory DIMMs. So this is a memory DIMM like this. So this is your memory, computer DRAM. And then we have some peripherals. We have some area for you to put peripherals. So the most noticeable peripherals nowadays is this, the graphics card. So if you have a graphics card, you pretty much need to put it here. And under the graphics card, there's also in a graphics card there's also a heatsink. And if you tear it down, you will see the CPU chip here. And also you can put a solid state drive like this one onto the computer somewhere, right? Onto the motherboard somewhere, right? So that's what a desktop computer looks like. So now I'm going to pass this component around because I know a lot of you are interested about this stuff. All right, so this is the processor, and be careful about the motherboard. And you can pass it along. And this is the solid state drive. Yeah, give me the complete stuff after that. All right, and this is the GPU. Just play with it. All right, so that's a desktop computer. And for server, they also stay the same in a way that if you look at a server, if you tear it down, you will figure out they also have a motherboard. On top of the motherboard, there are processors slots, and there are also memory slots like what you see in the computer that I just sent it out. There are also places for peripherals like GPUs and hard disk drive. And for smaller computers like MacBook Pro, you will find on its motherboard, there's also areas for a chip that combines processors and GPUs together. And there is also an area with memory soldered on the board. There are also areas for solid state drive soldered on the board and also modules for I/O. So far, you see every computer has an area for processor and memory, right? So, and the reason is because in von Neumann architecture, processors and memory are essential. And if you have an iPhone, right, it also have a single chip with stacked DRAM under their processor. And also have solid state drive as the persistent storage. So you will see, right? Although those computers, they are very different in form factors. However, they all have processors and memory. Well, you may have a PlayStation 5. If you want to sell it cheaply to me so that you can spare more time for work, contact me. And for PlayStation 5, you can also find a processor and GPU and a few DRAM. They solder it like a ring, which is a very fancy design. Although I kind of like feel like it's a waste of space. And then they also have the peripheral, like a solid state drive soldered on the board. All right, so smaller TV consoles like Switch, they also have processor, they also have memory, They also have space for persistent storage as well as I/O modules, right? All right, larger computer like a Tesla, right, which I just drive this weekend, and we feel like you shouldn't have it for a road trip because we are actually under the anxiety of out of electricity. So, but set it aside, right? For Tesla Model 3, this is the main control part of the car. It also has a processor which is powered by NVIDIA and DRAM, right? So you will see everything right now. If you want to have a computer system, processor, DRAM, or even storage, they are the essential parts. And they are everywhere. So we have a lot of different processors. For example, if you have a desktop processor, they are more likely to be manufactured by companies like Intel and AMD. If you have an embedded system, it probably go with NVIDIA or Qualcomm solution. If you have an Apple product, that will be Apple's processors. And we also have memory. It looks like we are living in a great world, but why are we still learning computer architecture? Why there are still research in computer architectures? Because there are challenges. So regarding the challenges or advancement of computer architecture, who do you think would be the guy pointing out the direction for us to keep fighting for? Moore, okay. Gordon Moore, he was the founder of Intel, and sadly, he passed away just a few days ago. And in one of his most famous thing that everybody know is Moore's law. So can someone summarize your understanding about Moore's law? What is Moore's law really about? Every 2 years, the number of transistors double. Anything else that you know about Moore's law? The amount of heat dissipated increases. That's not about Moore's law. What else? Okay, so you need to read a paper, right? So if you see the reading assignment that we have in today's lecture, we actually ask you to read the 1965 paper by Gordon Moore. So I know a lot of you like a summary, like a 20 seconds for a paper. So let's do this like TikTok video for you right now. So let's try to read more the cramming more components into integrated circuits in 20 seconds. So the first paragraph of the paper is trying to tell you that integrated circuits are increasingly popular, and they are well established, and they are very, very reliable nowadays, and they could be built really small, and they are easy to manufacture, and they are getting smaller and smaller. So look at this graph, right? So this is where the Moore's law really comes from. They say that, well, based on the year and based on the number of circuits that we can put into, the vertical axis is the log. So they are actually telling you we can double it every year, every 2 years, right? And heat is a stoppable issue. It didn't say it's increasing, it say it's a stoppable issue, right? And designing ICs could be easy. Done. We're done with Moore's law, right? So that's Moore's law really about, right? What Moore's law really want to tell you is that it's doubling every the number of transistor we can build in a fixed area of silicon doubles every 12 to 24 months. How is Moore's law going? You think it's dead? Close to dead? What else? You cannot say that because he passed away, right?
I think that they reached the limit how small
Okay. Changing materials. All right. So is Moore's law dying, or is Moore's law dead? Dying? Still working. Okay. So if someone tried to tell you about Moore's law is dying, that's not true. So look at the graph that I drew. And you can find this information on Wikipedia, by the way. So I pull out the information from Wikipedia. I draw the number of transistors per chip per area. And I draw this graph. Vertical axis is the log scale. The horizontal axis is the year. So if Moore's law is living well, you are supposed to see a straight line from the beginning to the end, right? And those dots are the number of transistor count for a chip, a commercially available chip with its number of transistors. So if I draw it from the beginning to the end and I make a line of it, magic, right? Every dot is not too far away from the line. Is Moore's law dying? If Moore's law is dying, you won't see this straight line. And look at the rightmost year, it's 2023. So I want to tell you one thing. In terms of the original definition of Moore's law is living very, 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 very well. Moore's law is still alive. We can still put more transistor in a chip for now. Moore's law has no trouble with it. What's problematic? So look at this. This is the NVIDIA's accelerator data sheet. What I want you to focus are actually these three rows. You can see the transistor count. For V100 is about 21 billion. For A100 is about 54 billion, more than double. And then for H100 it's about 80 billion. So you can see, and they are all using different manufacturing processes from TSMC. And it's getting a smaller node. So this is a proof that we have no trouble putting more transistors into a chip. But what really problematic is actually this line. The power consumption. See, for Hopper, it's really a crazy person. It's a crazy one, right? You need 700 watts to power that chip, right? So turns out that, well, for A100, you can still have a card like this. But for H100, it's actually a very, very giant chip that you need this shape. You need to build like a house, a very, like you need to build your heat dissipation like this to make it work out, right? So this is what's happening, right? So Moore's law is not dying, but what really problematic is the slowing down of Dinadian scaling, which means that with the shrinking of transistors, we cannot make the transistor less power consuming anymore. So it turns out that the power density of processor would keep increasing. So in late 90s, people already know how to use processor to put X, even though X are pretty expensive nowadays. Don't try to put it on your processor because it will fry for sure. And in early 21st century, people already know that the processor is almost as hot as the nuclear power plant surface. And if we keep producing chips like this, if we keep putting more transistor into a chip without controlling their power, then one day, before people can ever go to sun, the processor would be as hot as a sun. So, so that's what really constrains the performance of single processor core. So as you can compare from the graph that I show you, when the time that we know that we cannot produce more heat than the power density as a nuclear power plant, we start to slow down each single core performance. And then you see very limited improvement of single core performance. But in reality, we still have no trouble putting more transistors into a chip. So what do we end up doing is this.
The future is parallel. Single cores are not getting any faster.
All right, so the future is parallel. Single cores are not getting any faster. So what do we do is that in computer architecture, in the very beginning of the 21st century, each processor only have one processor core. But in 2005, we start to have the first dual core processor in the desktop segment. And then Intel in 2010 rolled out the first quad core processor. And there are also 16 core processor by Spark T3. That's actually a company previously called Sun and then acquired by Oracle later. And NVIDIA at the same time, they also have the Tegra 3, a 5-core processor. And also AMD at the same time, they also have a 16-core processor. So you can see that although we cannot generate more heat because of the constraint per core, but how we utilize this additional transistors that we can shrink into a chip is actually we put more cores into a single chip to maintain the performance we want. However, in terms of performance, you are now not getting performance from faster single cores, but more from the collaboration of multiple cores. So that's why John Hennessy and David Patterson, they were mentioning. However, even with that, there is still a limitation because those single cores that you put into a chip, they are still more power consuming. They are still less efficient. And if we want to power workloads like AI ML, it's not sufficient enough. And this is even true for GPUs. So what ends up is that nowadays we start to build AI ML accelerators. So you will see, like for Google, we built a tensor processing unit, and for Qualcomm, they have the Hexagon processor, which is an AI accelerator associated with the mobile phone processor. Apple has neural engine, NVIDIA has tensor cores. So those are the new trend in computer architecture that we need to spatialize the computation and realize them in hardware. So that's why we have AI/ML. That's where we are now. So if you look at the landscape of modern computer architecture, it's actually heterogeneous in a way that we not only have processor, memory, and storage, those conventional von Neumann architecture components, we also have GPU, FPGA, and tensor processing units as other processing units that are presented in your computer. So it's actually pretty heterogeneous. However, that also introduced a new problem is that because everyone shares the memory for data storage and everyone needs to synchronize data into the memory, and you also need to move data around. So there are also new bottlenecks there. But how good is our memory? So if you look at the performance between processor and memory, there's actually a huge gap between processor and memory now. So it's actually a problem. Okay, so some of you might be thinking about that. Okay, Professor, I know you talk about it's really important. I just want to be a programmer. Why do I care about it? Right? So let's first hear what these two guys said.
So the first thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster, right? That's over.
All right, so it used to be computer architects, we are such a nice group of people in a way that we make your performance like a dropping upgrade. So every time you just put a new processor, new GPU, we make your program faster. But as you can see, right now we have more parallelism. We have brand new architecture like AI accelerators. If your software cannot change, there's no way you can leverage the benefits of those. So it's in fact a time that we have to think about, given the computer architecture look like, how can we make our computer faster? But let's say those aside, even for general purpose programming, there are still tons of things as a programmer that you should know beyond computational complexity. So a lot of you think, well, complexity is the like a Bible or the guideline of programming design. However, I want to give you an example showing you that's actually not true. So this is the code that I'm going to give in a later demo. So can someone tell you or tell me what's the best sorting algorithm you have in mind in terms of computational complexity? And what's the complexity? Quick sort. What are the sorts? Merge sort. Okay, what's their complexity? N log n. Okay, so the first part is n log n, right? Okay, how about the for loop? What's the complexity of it? Order n. All right. I have a question for you. Now, if the option is true, what's the complexity of this pieces of code? And again, if the option is false, what's the complexity of this pieces of code? Log n. Okay, so will your program be faster with the code, with it being sorted or not sorted? According to what you have learned in complexity, which one would give you lower complexity? Sorting it, not sorting it. Not sorting it. All right. So if the option is set to 1, it's an order n log n algorithm. If otherwise, it will be an order n algorithm. So if you just learn things from the the algorithm teacher, what you will feel that, why am I doing the first part, right? So now I'm going to give you a demo. All right. Okay. So all right, so this interface is called Python Notebook. If you have never used it, you will use it a lot in the future. So this is a new way of people do data analysis these days, and Google also have a copycat of it called Google Colab. So it's a very essential tool that you need to learn in the future. So first, in this program, I have a function called calculate sum. It's exactly implement that order n part of the program that I show you. And then I also have the complete program here. So the complete program is essentially that, like what I show you is that, well, I initialize an array of data like this here, and then I will sort it or not, depending on the value of the option. And then I calculate the sum of the complete array. So that's the code. Now let's run it. So first of all, we have to make it so you know that I just built a program right now. And I have first, this is array sort, which is so first we have 3 arguments. The first one is the size of the array, and the second one is the number of iterations, like how many times I want to go through this array to generate a result, and so that the total amount of time is significant enough for you to compare. And the last argument is actually passing the value of the option. So right now, the first case, we set it to 1. So let's see how much time it would take. Okay, if I set it to 1, it will take 0.177 seconds. Now, let's go through the other case let's set it to 0. All right, so if you set it to 0, which means that we don't sort, it actually takes 0.6 seconds, which is 4 times more than the n log n algorithm. Isn't that counterintuitive? Isn't that counterintuitive? Are you ready to throw your algorithm textbook away? Let me tell you one more thing. Okay, so sorting is very important part of this, right? And you guys say that, well, we have quick sort, and I don't think we need to remind you too much about the quick sort. And another sort that I'm going to introduce is called Bitonic sort. The Bitonic sort is actually an algorithm that, if you look at this one, it actually would have higher complexity than quick sort in a way that its complexity is n log square n. So it has one more log n compared with quick sort. So now let me run this on NVIDIA GPU. Well, so sorting sorting an array. So here I hard coded the number of arrays. The size of array is a sorting 32 K elements. It only takes about 0.5 seconds on the NVIDIA GPU. And the reason why it takes so much time is because on this GPU, you have to copy your data from your memory to processor to the GPU. So it takes a while before you can start running it. And now I have been running this quick sort on GPU for a while, which is an unlog n algorithm supposed to have lower complexity than the Bitonic sort. And I'm running out of words that I can say at this moment, but I haven't seen the quick sort finish. And yeah, and finally it finishes in about 30 seconds, right? So another thing, right, that you will learn is that, well, sometimes complexity, if it doesn't allow you to utilize the parallelism on GPU, it's not going to work. And some of you might be questioning me that, well, professor, you must use a very outdated GPU. Yes, I'm using a GPU that's 2 generations ago. It's RTX 2080, which is still a very powerful GPU, right? So you know that this is a general problem in GPU. So here's the thing. When you are designing your program, complexity is not the only thing you should care. In fact, computer architecture is very important. So why computer architecture is important? I don't know how many of you ever watched this anime before, but I really like it. So there is always a section before go to the commercial, is that guess who I am, right? So most of the time when you see this tail, you will think that, well, right now I have is like this, but actually you might have this, right? So here's the thing, right? If you have Pikachu, electricity type skills are the best ones to attack, right? But if you have this mimic, right, you have to think about if there is any spiritual type of attack you can make, right? So the key thing is this, right? The good thing about knowing computer architecture, being a programmer, is that you know what kind of bits that you are dealing with, then you can better utilize that bit. All right, so that's why we need to learn computer architecture. And all right, so here's the guideline. In CS203, unfortunately, this is not a class that can tell you how to write code very fast. So it won't help on your lead code, but it will help at the rest of your life in a way that we are going to let you know how to write faster code. So that's the agenda of this class. All right, so then how can we achieve this? So we are going, in this class, we are going to cover 4 big topics. First part about performance, the second part about memory, then we are going to talk about processor, and finally, parallelism. So these are the 4 main topics that we will be covered in this class. And we have a tentative schedule that you can already find on the class website. We will cover these 4 topics nicely throughout this quarter. And we will, and we have, well, but depending on our discussion, sometimes we may have to change the subject, and you need to complete the readings that are assigned before every lecture. All right, so finally, let's talk about the learning experience of CS203. So first of all, this class, we have 2 parts. The first is the in-person lecture experience. So some of you might be thinking about, hey, it's COVID-19 pandemic. Yeah, I know about it, but you know, we have to live with it. And in fact, a lot of companies are calling staff back nowadays. So a lot of you are still under the impression that, okay, I can work hybrid from anywhere. But what I want to tell you that is not true anymore. It's not true anymore. Don't dream like that. So it's better that you get used to the normal life. And but what I want to provide you is something different from conventional lectures. So one of the reasons why people don't like to go to conventional lectures like today's lecture, because it's mostly like watching a TV program, TV news, that you have an anchor or you have a host who try to say a lot. And for me, for you, it's more like, okay, I just watch it and I get sleep, right? So you don't like that. I don't like that either. So what I really like is that our lecture should be a game show in a way that I'm the host and you are those guys who are participating in the game. So, but how can we make that happen? It's actually our teaching method called peer instruction. So in this class, again, if you want to participate in a game show, you must do some pre-training. You want to do some preparation, right? Like, I don't know what's your favorite game show. I like those Ninja Warriors shows in a way that you will see how people challenge those difficult things, right? But you cannot imagine someone would never prepare and go to that show. At least you have to go through that route once, right? So same thing here is that we want you to prepare. And I don't know how to force you prepare except for having reading quizzes. So that's why we have reading quizzes. And then during the lecture, I will have some pop-up questions that I would ask you to think first individually and discuss in a group like we just did today, and then we will have a whole classroom discussion afterwards. So the learning process is pretty much read, think, and discuss. And so in this, we have to have a reading quiz. And how do we get your response? Is actually from a software called Poll Everywhere. So you need to get it set up before the lecture next time. And what you need to do is that by answering 50% of a clicker question in your class, you get 5% of your final grade. So that's a pretty good deal. And I already set the threshold really low to be just 50%, which means that you can be absent in half of the time. Or if you don't want to talk with anybody because you think everyone is like a virus, fine, right? Just think individually and don't click on the group once. You will be fine too, right? So, but what I really want you to do is that at least think once before we have these answers for you. And that will really help you a lot. All right, so during the lecture, you will need to set up the Poll Everywhere and log into the app using UCR Net ID at ucr.edu and join this website before the next lecture. All right, so grading breakdown, we have 15% in reading quizzes, 5% in class participation, assignments throughout the course, 25%, midterm 20%, and 35%. And the second part of our learning is actually using Jupyter Notebook. As I said, it has been intensively integrated in modern data analytics systems. So it's definitely a good thing for you to learn. And another good thing which I like is that you can make your assignment really interactive. So for every assignment, the very first thing to do is that you have to go to our course webpage. That will give you the link of the web, like for you to create the assignment, for you to access the assignment. So let me see if I can show you a demo for them. Okay, probably not. All right, so maybe we can do this. So for each assignment in the very beginning, all right, here's my browser. Okay, this is Microsoft. What you will do is that you will go to our course webpage. Okay, so if you don't know where our webpage is, you can just go to my website at UCR. Let me see, what do they give you? Okay, so Bing search is not a good one to figure out where is that. All right, so if you go to my webpage, there will be a section called teaching, and from there you can find our course website. And at this course website, if you click the assignment session, they will give you the link of the upcoming assignment. So just click this one, and then it will ask you to log into your personal GitHub. Don't worry, just accept that. And then it will ask you for authorization, but it will let you accept the challenge, right? So what you will have to do is that, okay, you have your own GitHub repo created for that, and visit that. There are actually pretty clear instructions how to start with your assignment. So you will see we have very, very, very complete instructions there, and just follow the instruction and you should be good. So for example, the very first thing you need to do is to log in your the data hub, which is an infrastructure that I built for this class. All right, I hate this. Okay, I will skip this part now. All right, but yeah, try to do that, and it won't be that difficult for you to do that. All right, so so with that, for every assignment, what you have to do is about the same. Just go to our course webpage and then click the invitation link for the upcoming assignment and log into our data hub and follow the exact instruction that we put on the Python notebook and the README, and then you should be able to do it. So that's the assignment. And for this class, we use GitHub and GitHub Classroom. So for those of you who are interested about software engineering, you should definitely learn GitHub very well. And this is a very good chance for you to get familiar with that. And for the course infrastructure, we have bare metal servers in the cloud for you to play with, although in a certain degree. And the reason why we allocate those machines for you is because we want you to use the Jupyter Notebook designed assignment to measure the program performance and even the power consumption and the detailed hardware behavior. And it's unfortunate that the virtualization would mess that up. So we can only give you the bare metal machine, which may be less stable if some of you try to make some malicious code. So please don't do that. And each lab and each assignment is using Jupyter Notebook, and it's, as I said, Google's Colab is basically a copycat for that. And if you haven't used Jupyter Notebook before, this is not that hard, and it's a good chance for you to learn it. And again, we have the dedicated service server for you. And each document is pretty much like this, that you can run a few commands, and then the commands would allow you to plot things like this. So your assignment turn in is just like stuff like this. So it will be very, very fancy. And in each assignment, well, unfortunately, except for the first one, which is due in the next Thursday, every assignment will be pretty long, but I will give you around 2 weeks to work on it. So start early is always a good idea. And again, because the server is shared among you guys and we have 80 students. So if you are late because of the server is crowded or busy, that's definitely not a reason. That's definitely not a reason, because I give you around 2 weeks and you know this is going to happen. So that's what is not a reason for late submission, and there is no late submission acceptable in this class. And we will give you a command line tool to run most of the job, and you will learn most of it through the Jupyter Notebook. And then in each assignment, there are 3 parts. First is the PDF submission through Gradescope, and then the programming assignment, which we will use Gradescope's auto grader. And another good thing about the Gradescope auto grader is that we will compare the code. So so if there is any cheating cases, I will just send it directly to the academic integrity office, which I did last year, and it's a very good experience. And then we will have a post-lab survey which we want you to give us some feedback so we can make it better. So those three parts are essential. And because we are running out of time, so I would skip the walkthrough part and I will try to make a video later. Now, logistics. So again, for this class, we have lectures, and I will try to put our live streaming recording, but as you can see, this classroom is not very reliable in the technology. So I don't know how good I can do, but I will try my best. And the slide schedules are all on our course webpage, discussion on Piazza, and reading quiz and check grades on eLearn. And if you want to submit assignment, it's all through Gradescope. And the website has schedule, and we also have a calendar on the website. So subscribe that, you will know our most up-to-date office hours. And here is me. So most of the time I'm like the right-hand side, but sometimes I would do some other interesting stuff. So don't be surprised if you find me in the Anime Expo this July. All right. So here's our TA, Guanjie. Do you want to say something to our students?
Hi everyone, I'm Guanjie Xu. So I'm gonna be a TA for this quarter. So we have 3 TA office hour every week. So if you need any help, you can come to the office hour.
All right. So is the office location determined?
TBD, yeah.
Okay.
I will figure it out.
Okay, so the office location, if we figure that out, we will put in a calendar. So definitely subscribe to the calendar if possible. All right, so if you want to find your grading, that will be on the eLearn. And most important thing, I hope I don't have to mention that a lot, is that don't cheat. And again, so in the past, I will try to talk with students a lot, but I don't feel that's really a good experience for me. So that year, one thing I did is that I just sent everyone to integrity office, and that will save me a lot of time. And if you think you are innocent, it's a good idea to explain with them. All right. So a few things that I want to mention. So Piazza are the places to ask questions about assignments, and you get lost on assignments, that's when you need office hour. And there's no late submission, again, and again, no late submission. And if you are going to miss the class, don't send me an email because we already allow you to miss the class for 50% of the time. And we try our best to record everything in my YouTube channel, so go subscribe it. Also, it's a good idea to come to class because it really helps. And if you have issues with eLearn or Data Hub, please contact the campus IT. And if it's Data Hub related, contact me. And if you are sick, well, again, 50%. And if you have some other issue that we need to accommodate, let me know in the first 2 weeks. And the auto grader or something, try to post Piazza. And some of you are arguing why we really need a textbook. There are quite a few reasons. Even Jeffrey Hinton tell you it's important, right? And we have many different resources. I know it's a bit annoying that we are spread out in different websites, but unfortunately, there's no good one-fits-all solution. And that's actually a pretty good startup idea. If you want to start one, I'm over it. And finally, the term of service. Most of you never read it, so just click it. All right. So I've been teaching many different classes in different schools, and I enjoy teaching, and I would like to reinvent every of your learning experience. And in the past, I have been teaching in UC San Diego and NC State University. And since I moved to UC Riverside, there is a new challenge called UC Zoom that we have to host as another UC campus. But fortunately, I think we are kind of like get rid of that. So hope by the end of this quarter, we can take a photo like this as a group. All right. So thanks for attending to the first lecture. I will see you on Thursday. And don't forget, we have a reading quiz due before the lecture on Thursday.